Hey guys, it's Mr. Moberg. This screencast is about how stars change. Specifically, we're answering the essential question, what is the life cycle of a star? Now, in the end, what do you as a student need to know? You need to be able to identify all of the different phases of a star. You need to be able to describe the order in which they change, and you need to be able to talk about the difference between a high mass star and an average to low mass star and what their life would be like differently. This image summarizes the life cycle of a star. In the end, after this screencast, you should be able to sort of explain all of these steps. But before we do, I kind of want to just give you an analogy about how stars change. So stars go through a life cycle, and not that it's an exact connection, but kind of like how people change over time. You know, you have your baby, your toddler, your younger child, and as you work your way through life, you go through changes, and so do stars. Depending on the mass of the star determines a lot about its ending and what happens to it. I'm going to have you watch a video right now. It's about 4 minutes, and it goes through sort of all of these different phases. It's going to give you some good images and some good descriptions for the life cycle of a star. Afterwards, we'll take some notes.
They begin in clouds of dust and gas so far away that we would need 100,000 years to reach them. Gravity gathers hydrogen gas and particles of dust, and the clouds grow more dense. Squeezed tighter, the hydrogen heats up to a fantastic 10 million degrees Celsius. Nuclear fusion turns hydrogen into helium, and the fire ignites. A star is born. Astronomer Michael Scharrer compares a star's life cycle to our own.
Stars are born, age, evolve, and eventually die, just like people. They have a regular life cycle. During the entire life of any star, there is this delicate balancing act because gravity is always at work trying to crunch the star down into a small point, and the high internal pressures are trying to blow the star up and blow it apart.
Of course, a star may live for billions of years, and stellar age has nothing to do with lifestyle or heredity. It's all about size. Smaller stars burn cool and dim. When their fuel burns out, they just fade away. A medium star, like our Sun, will burn steadily for some 10 billion years. But when it finally runs out of hydrogen fuel and gravity grips the core harder, the star grows hotter and the outer layers puff up, engulfing nearby planets in its fiery demise. Finally, the outer layers blow off into space, and a dense solid core remains. This white dwarf is a dying star. A bigger star, say twice the weight of our Sun, lives hot and dies young. It burns through its fuel in just millions of years, and it doesn't go quietly. There's more material here for gravity to constrict. The star goes out with a bang called a supernova. Gravity packs the remains into material far denser than white dwarfs, called neutron stars. A teaspoonful of this stardust weighs more than a cruise ship packed with people. Some enormous stars that have gone supernova become so dense they turn into black holes. Think about it. A massive explosion leaves gravity unchecked, and matter is squeezed into something unseeable, stretching for miles, and weighing incomprehensible amounts. Got it? Invisible but deadly, pulling in matter all around it. Even light can't escape. Not to worry, supernovas are rare. A galaxy like ours, of 100 million stars, may experience only one exploding star in a century.
Now that you've watched that video, I'm going to try to break those notes down a little bit for you. Wherever you are taking notes, you should probably have 2 sheets of paper side by side. I think there's possibly a section in your notes for this. And you're going to use both pieces of paper side by side. They're going to carry on and flow from one to the other. Hey guys, I'm going to walk you through some notes on the life cycle of a star. You should have your notebooks opened up to these two pages kind of side by side. On the left, it should say something like life cycle of a medium-sized star, and on the right, life cycle of a very large star. We're going to take these notes kind of on a combined page because both stars start out as the same thing. Now, as you watch this, please feel free to pause the screen at any time if I'm going too fast to make sure that you keep up with the notes. I'm going to focus right now on just the main names for the phases, and then as you watch the rest of the screencast after these notes, you can actually add notes kind of in the empty space here to try to get at least one thing about each phase or stage that stands out. So let's start. All stars start out as a giant cloud of gas and dust. And again, this kind of overlaps both pages in your books. And that is called a nebula. As that gas and dust starts to compress and come together, it forms a protostar. It's like a baby star. There's still some haze around it, so you can kind of draw that in here. And again, this kind of overlaps both pages. So let's call this a protostar. Now, after the protostar phase, depending on the mass, it's either going to go this direction or this direction. So let's pretend the mass is a medium or average sized star. After that protostar phase, it is going to turn into a main sequence star. And this is kind of like our sun. Our sun is sort of an average main sequence star. This is where the star actually spends most of its life. This is like an adult star. This is where nuclear fusion is happening. It actually started in the protostar. And then after that main sequence star, when that star starts to run out of energy, fused together, it turns into a red giant. It swells up to get much more massive than the size that it is. And after a little bit of time, that red giant sort of starts to run out of fuel too. And all of that extra gas sort of drifts off of space. And we end up with the core of that. The tiny little circle there. And that's called a white dwarf star. As that white dwarf star cools, it's going to end up as a black dwarf. That, again, is the path of a medium-sized star. That's kind of the dead end for that. Now, if we have a massive star, after that protostar phase, we get, actually we use blue here because blue is a hotter color and this is what they tend to be. We get a massive main sequence star. Again, this is like an adult star. It spends most of its life in this phase. After that star starts to run out of fuel, can't fuse the atoms together anymore, it turns into, similar to the other phase, but much bigger, a red, not a red giant, a red super giant. And as that expands and starts to lose energy and then starts to come in on itself, it has kind of a big finale, a big ending in that it explodes as a supernova. Giant explosion. Now, after that supernova phase, there's really kind of three outcomes that come as a result. After that supernova, it can turn into, if big enough, a black hole. If it's not quite big enough, but still has a lot of energy, it can turn into a really dense, really, really hot star called a neutron star. Talk more about those in the coming up in the screencast. Or some of that gas and dust, as in that explosion is given off, some of that can form back into a nebula and actually repeat this process and form a whole nother star. So it's all those ingredients that don't get wasted, they can get turned back into another star. Notice it's kind of a cycle. This can move on the continuum and they can turn back into new stars. At any given point, a star can find its way on anywhere on this chart, depending on where it's at in its life. All right. Now that you're done watching and taking those notes, let's break down each phase specifically and what happens in each phase. All stars, no matter what, start out as a nebula. A nebula is a giant cloud of gas and dust that's mostly hydrogen and some helium. And what happens with it is first of all, they look really cool. And depending on the type of gas that makes them up is going to determine sort of the colors that you end up seeing out of it. Here's a few more images of that nebula. This is obviously an artistic depiction of an Orion Nebula, not a real picture. So as that gas and dust sort of starts to come together, gravity gets hold of it and starts to pull on it, which is what gets us to our next phase, protostars. Protostars, if we're looking at that life cycle example, are kind of like your baby stars. It's the moment that baby gets the heartbeat and the moment that star starts to do nuclear fusion. This is where, just a reminder on nuclear fusion, this is where atoms, in this case hydrogen, are fused together to make helium, and this is what light is given off as a result, and a whole lot of energy. Here's an artist depiction of what the forming of a protostar might look like. You can see here in the center where that fusion has started to take place, and around the planet, all of the extra dust and debris are revolving or circulating around the center. And this is the theory of how our solar system came to be. All that dust and debris came and started forming into planets and moons and other things. After the protostar stage is the main sequence stage. This is where most stars spend most of their life. Our sun happens to be here right now, and for the sake of this next course I'm going to take, we're going to take a look at the left-hand column here, which is where the average star life cycle is. Something that I think is somewhat interesting about main sequence stars is the lower the mass of the star, the longer that star lives. Fortunately, our star has a little bit of a lower mass, and so it's going to live a relatively long amount of time. I kind of like the analogy here of comparing a Prius to a Hummer. A Prius is smaller, but it gets really good gas mileage. It's efficient, and it doesn't use up all of its fuel at once. That's what our sun is like, and that's what an average mass star is like. Hummers, on the other hand, which we're going to talk about in a little bit, don't get very good gas mileage. They use their fuel up quickly, and as a result, live a little bit shorter of a life. Our sun right now is about 5 billion years into its life, which is about, scientists predict, halfway through its life cycle. You can see this image here. I just wanted to explain it. Our sun started out as a nebula, which started to come and contract together to form into a protostar, where nuclear fusion started to happen. And now we find ourselves in the main sequence. As we continue the progression of what our sun will do, we have quite a bit of time left in this stage, and eventually our sun is going to swell up into this next phase, which is called the red giant, and I'll talk about that in just a minute. The red giant phase. Red giants are exactly what they say they are. The one thing that I think is pretty cool about the way that these star phases stages are named is that they're not scientific challenging names to remember. It's red and it's giant. This image compares a red giant to what our sun is right now, and you can see that it's going to swell up significantly. The reason this happens is because the sun starts to run out of hydrogen to fuse, and when it does that, since it's not super massive, it starts to become frustrated, and it starts to swell up as a result. In the red giant phase, the volume increases and the temperature decreases. Starts to swell up. You can see here in this image that the Earth, this is the Earth's orbit, and the sun, our sun will scientists predict swell up all the way to the orbit of our sun. What will happen to Earth when this happens? I'm going to show you a couple-minute clip about how that works.
For the sun, but what about us? Of course, the Earth won't fare very well during all this. It'll get cooked before the sun even becomes a subgiant, and by the time the sun is a red giant, we'll be good and fried. The average temperature on our planet will be so high that it'll melt rocks, and in a sense, it'll look much like it once did so many billions of years before, when it first formed. A molten ball of rock. But it gets worse. When the sun expands, it'll reach a radius very close to the size of the Earth's orbit now. Does that mean our planet itself will be consumed by the sun? Maybe not. As the sun expands, remember, it loses mass. That means its gravitational pull will weaken, and Earth will move out from the sun into a bigger orbit. If things work out right for us, the Earth will back off faster than the sun expands, and we'll avoid finding out what it's like to be inside a star. Due to a quirk of physics, if the sun loses more than half its mass, its gravity will decrease so much the planets will no longer be gravitationally bound to it, and they'll be flung into interstellar space. I'm not sure that's any better for us. Either way, the Earth will have been long dead, and hopefully humanity will have figured out the trick to interstellar travel by that time. All those Earth-like exoplanets around younger stars will look pretty nice in a billion years or two. Mind you, this isn't happening anytime soon. The Sun won't become a subgiant until it's nearly 11 billion years old, over 6 billion years from now. The first red giant stage happens when it's over 11.5 billion years old, and the second stage a half billion years later. This is a long, long time coming. If the Sun had more mass, it could avoid this fate. A star with about 8 times the Sun's mass can. It has enough mass to squeeze those carbon nuclei hard enough to fuse them together. Those high-mass stars have a much different and far more explosive fate than lower-mass stars like the Sun. And trust me, we'll cover that in lots of fun detail soon. And while this all sounds very bleak, not all is lost. This is all part of the natural cycle of the universe. And in fact, we wouldn't be here at all if it weren't for the way stars live and die. Be thankful for what you have, and that we can not only observe it, but understand it too. Today you learned that very low-mass stars live a long time, fusing all their hydrogen into helium over. More massive stars like the Sun live shorter lives. They fuse hydrogen into helium and eventually helium into carbon and also some oxygen and neon. When this happens, they expand, get brighter, and cool off, becoming red giants. They lose most of their mass, exposing their cores, and then cool off over many billions of years. Crash Course Astronomy.
Hopefully that video was helpful in kind of summarizing how stars get to that red giant phase, and also gave you a little bit of information about what might happen to the Earth someday. So let's move on to a couple of the last stages, white dwarfs. White dwarfs are, again, kind of what they say they are. They're white and they're really, really small. As I look at this image, I see that tiny little speck right there. That represents a white dwarf. White dwarfs are dense, tiny, and really, really hot. Right now, our sun is millions of times the size of our Earth, but someday, when only that white core, that really hot white dense core is left, our sun will be about the size of our Earth is right now. The last phase that actually doesn't show up on this picture is the black dwarf phase. Black dwarfs are white dwarfs that have cooled off. They are no longer giving off as much heat, and so they aren't giving off light anymore. Let's take a look now at that right-hand side where we're looking at massive stars. These are stars that are going to be 8 to 10 times the size of our sun, so significantly larger. So this next phase after a protostar. So all stars start out the same way. They start as a nebula, they turn into a protostar, and then they turn into a main sequence star. And this phase for massive stars is a little bit different. I gave that analogy earlier about smaller stars living longer lives and how larger stars don't live as long. Here's why. Because they're so massive, they end up using a lot of their fuel, which is hydrogen and helium, and they fuse a lot of those atoms together quickly, which uses up their source of energy, and they end up changing quite a bit sooner. Here's an image of a blue main sequence star. It's blue because it's really, really hot. And again, we mentioned the higher the mass of that star, the shorter the life. Just like with average size stars, this is where they spend most of their life. As those main sequence stars start to run out of fuel, just like the other side did, it starts to swell up into a red now supergiant. Not just giant, but red supergiant. It's going to continue to expand and get really, really big, and the volume is going to increase while the temperature goes down. This is one of the reasons that they turn red. We learned earlier this year that red wavelengths are longer and therefore carry a little bit less energy. There is definitely a connection there. Supernovas are sort of that big finale ending where there's this giant explosion and a whole lot of energy and heat is given off. Here's a picture of a supernova that's about 8,000 years away that our satellites have looked at. And in this space, the temperature can reach up to 100 billion degrees. In this really high heat and temperature, some more fusion can happen, and the star in this last phase has the ability to make even more and more elements that it wasn't able to make before. After a supernova happens, there's kind of one of three things that come out of it. Either a black hole, a neutron star, or more gas and dust left over for a nebula. So let's take a look at a neutron star. Neutron stars are the densest and some of the hottest stars that exist. In fact, 1 teaspoon of a neutron star can weigh up to 100 billion tons. So it's really, really tightly packed together. You can see in this image, this one is sort of spinning and pulsing, shooting out waves of energy. A black hole is another option. Black holes happen with stars that are about 30 times the mass of our current sun. We actually can't see black holes because they're not giving off light. The only reason astronomers know black holes exist is because when they're looking into outer space, they can see places where there is no light. Black holes have an extremely high gravity, and they pull in all light and matter around them. We're not going to talk a lot about black holes right now, but I do know that they're a super high area of interest. We will post some resources for black holes, so I would encourage you to check some of those out if you are curious and learning more about them. The last product that can come out of a supernova is more leftover gas and dust for another star to form. That's one of the reasons that we call these life cycles of stars, because after they die, they can repeat that process and start over again and form possibly a nebula. Let's review just a few things we talked about. Stars are always changing. The change depends on what the star is fusing. We talked about hydrogen and helium being some of those main elements that stars fuse together, and when they run out of fuel, they start to change into other stars or other stages. One of the things that you should know at this point is about one main fact for each star stage. At the end of this screencast, I'll post that at the end here, and you can make sure to pause the screen and make sure you have something written down for each. And the other thing that we would like you to know is the order of both high mass and medium to low mass stars. You should be able to basically trace the steps of all of those lesson. I want you to pause your screen right now. Make sure that you have each of these notes kind of written in on your notes diagram. This would be a good place for you to refer back to and study. Now that you've finished, I'm going to ask you to do one more thing. Take your notes and try to explain the life cycle of a star to someone nearby. I find that talking through this is really helpful and can help your memory. Other things that you might want to try, there's a quick 2.5-minute recap of all of the life cycle of a star that I'll also post. And there are also a number of games and other websites that you can be looking at to strengthen your understanding of the life cycle of a star. Thanks for watching.